Yeah, by the way, it was thank you for again for asking. So just here there is a slightly non-clear moment that should be explained, and this should be done as the series of exercises. So here that was as for the theorems that we have, so these zi's were actually the images, of fi. So just of corresponding yi to g. And notice that this product, so I claimed that zi, which is an images of this one in G, is constructible, but we didn't formulate these four constructible sets. So here you have a product of constructible sets. So I want to use the following. So I want to write down the real morphism of algebraic varieties. So you are writing down yi1, etc., yik, and the map to G is just mapping yi1, yik into the product of fi1, yi1, etc., fik, yik. And you see that it is a map of algebraic varieties, so this image is precisely zi and is constructible. But of course, why constructible subsets are interesting? Because they are closed under the maps of algebraic varieties. So the constructible subset is always lie inside some variety, so because it is considered as a subset. So let us take the morphism of varieties. So this will be exercise. So morphism of varieties, algebraic varieties, and z is constructible here in X. Then I claim that f of z is constructible. Yeah. And so apply this exercise to get that if you have collection of constructible subsets, so then the product of this, so they are constructible in the group, constructible zi inside the group G. Then the product, element-wise product, is also constructible. You have to use this one. Yes, so you have to, the idea that you have to see which, you have to produce the map of algebraic varieties where this should be a constructible subset. And you have to apply this exercise.
So we used it in our code?
Yeah, we used it. I mean, you can use either here, because initially we were taking the images.
So we can reformulate our conditions such that they are like not images, but
you have so this proposition can be reformulated as follows. So you have, let me reformulate it, but I think this is just less. It is to refine what was used in the proof, and not. I do not see quite much practical sense of this. So if you have collection of z alpha is collection of constructible sets of constructible subsets of G such that E belongs to Z alpha for any alpha, and the unit of the group, and Z alpha is closed, is irreducible, then the group generated by Z alpha is irreducible. Yeah, for all alpha in some set. Yeah. So just is irreducible and closed. So is algebraic. So it is closed algebraic variety and algebraic subgroup and irreducible. That is irreducible. Yeah. Okay. So so why I bother about so this lemma actually we will need this rather rarely, but in a very important place. So that's why we spend so much time on this lemma. So the idea is that just in algebraic groups or in Lie groups, you usually want to introduce also good analogs of the notions which are valid for finite groups. And for finite groups, you have, or abstract groups, so for abstract groups, you have the notion of, first of all, the commutant, taking commutant. And also you have a notion of, well, solvable groups, nilpotent groups, etc. So, but the problem, problem number 0, so that what is commutant, so you want to pick up the commutant of two elements. And of course, the product is of commutants, just of commutators is not a commutator. So the problem is that this doesn't form, this subset doesn't form the group. So this group is just a minimal group generated by this by commutators. Yeah, so the group generated by commutators. Yeah, by commutators.
So we will use this proposition.
Yes, to prove that it is will be a group. So, but the problem now that so we have fixed the problem, set theoretical group theoretical problem, but now we are in the we got new problems so that this could be not algebraic group. Yeah? So this could be not algebraic group a priori, not algebraic group. And surprisingly, yes. So this, and now you have the difference between Lie groups and algebraic groups. So in Lie groups, commutant is not a Lie group, a Lie subgroup. Yeah? So it is so for in smooth category, of Lie groups. So commutant can be not a group. So is not a Lie subgroup. Is not a Lie subgroup. It can be not closed. So instead of taking this object, you can take the so-called Maltsev closure. But this is different theory. And in our case, at least, our lemma gives us a very nice observation that just suppose that G is connected, so is reducible as the variety. Then you have commutator map. Yeah, so you have the commutator map to G, which is just writing down our commutator. And this gives you that this image is constructible set, and put it to be Fi, and put Yi to be image of Fi. So the group, so the subset generated by commutators. Then of course, then of course you can the G times G is generated by products, and you can pick up so you can apply our lemma to one actually to one subset, yeah, so one constructible subset. So what?
I didn't understand how does a commutator generate it with Y's?
I mean this commutator. I mean, so this is a commutator. So this. The elements of this are this one, the elements of the second one is this one, etc. And
the lines are subsets, and we generate
Попробуйте по-русски спросить.
Короче, правильно я понимаю, что в Y у нас получается множество равное коммутатору, но оно не группа, а просто множество.
Просто множество.
Да, и благодаря предыдущему мы можем перемножить их все и получить алгебраическую замкнутую.
Да, так и есть. Просто надо взять, ну, то есть образ вот двух элементов, ну, вы берете два элемента, отправляете в G, этот образ, это конструктивное, ну, образ просто G на G, да, ну, то есть Y это, да, Y это G на G, да, ну, в смысле, в нашей лемме было, что у нас были множества Y и T и отображение F и T. Ну, именно для этого я и сформулировал это все в таком виде. Да? Ну, и мы породили образами H so notice that this Y contains unit, yeah. So E belongs to the image of F of Y. Yeah, so you have y here, so E belongs to f of y, and you can, yeah, so you generate the group by the products of I. I mean, you have only one element here, yeah, so just in our element you apply lemma.
But can't we say that JK is generated by y itself, by image of f?
Yes, by one.
But what is this product? Y times y times y?
How many times should we multiply?
I mean, it's not clear. I mean, it happens by just. It's not clear because I mean, just you have to write down the estimate for dimension. Yeah. So yeah. So notice that. But you can ask, yeah, so your question is good because you can write down the estimate, yeah, so you can precise estimate for this number of generators that you have to pick up. Notice that first of all, how to get, so in our ну, не камера. Это хорошо. Yeah, so in our lemma, we had collection of the sets Zi. Yeah, so just EI1, etc. EIK. Yeah. So first of all, you have to understand how many elements we have to take in I to get the set Z of I. Till, so such that its closure is maximal. Yeah?
So it's dimension.
But you have only one element y. Yeah, so and here you have you can bound it by by dimension of G. Yeah? Because at each step you can add the Zi, which increases. So you have collection of I1.
If nothing increase dimension, then we won't else choose anything.
I mean, all the time you are adding the element that increases dimension. Yeah?
Image of irreducible is irreducible.
Yes. So the number of elements you have to take here. So at each step you can choose the just in such way you can choose the element in such a way that you are strictly increasing the dimension. So just the bound is by dimension of G. Yeah? And the bound of the number of I you have to take. Yeah? And then you have to notice that you have to notice that next, in order to take the group, yeah, so you have to take twice Zi. Yeah? In order to get that it is equal to the closure of Zi, so you have twice the dimension of the group for the number of generating elements. So. So yeah. So next, I want yeah. So here you see that that commutant is well-defined group. Next time we shall discuss something about connected components. So in general, there is of course proposition that if G is algebraic, then a commutant is also algebraic group. So this will be it is it's more complicated. So here you have to discuss some connected components. You cannot apply this lemma directly, but it should be discussed via the previous lemma that we proved, and we are discussing the sets of connected components. Irreducible components. Yeah.
It's not about connectivity.
Well, for the group it is the same, because if since the intersection of connected components form the bed set. I mean, if the connecting, if you have the intersection of irreducible components, they form a bed set from the viewpoint of the group. Yeah, so they form non-smooth set, and the smooth set should be invariant. So the group, I mean that.
So in group, reducible components can intersect.
In the group, reducible components cannot intersect. So just so exercise in the group, irreducible components are not intersecting. Yeah, so yeah.
Is it right that an algebraic group may be a non-smooth, a singular algebraic variety?
A singular algebraic varieties cannot be the group.
So what is, why do we have a question about intersecting of components? I mean, I thought that every algebraic, smooth algebraic variety consists of only one component.
Yes, yeah. It could, I mean, it could consist of several components, but they are not intersecting. Yeah. So So I wanted to discuss the following proposition about action. So let me call it locally finite property of the actions. Of the actions on the set of regular functions. Yeah, so here you have the following, so you can ask the following question. So suppose you have algebraic action now, so this is algebraic variety. Yeah, so you have a natural map on the functions. So if you have f of x, so you have the function, the action on the function, g inverse of x. So this gives you action on the set of regular functions. of k of x. Yeah, so the set of regular functions is the following. So you cover your variety by the charts. Yeah, so you you consider the function is called regular if it is called if it is regular on its chart, on each affine chart. So if you have this action, you can, I mean, of course, so in general, this is a quotient of polynomial algebra, or even so with on a affine space, it is just polynomial algebra. So it is clearly infinite dimensional. Yeah? But the question is, for example, if you have affine just the polynomials, and you act by the linear transformation of variables, then of course it is clear that the degree of the polynomial is preserved. Yeah? So if you are acting on the corresponding variables, the degree of homogeneous polynomial, for example, is preserved. So you see that your space is decomposed actually in the finite dimensional spaces, in the direct sum of finite dimensional spaces, which are stable under the action of G, of linear transformations. And here the situation is the same. So the proposition for any f inside k of x, there exists a finitely dimensional vector space V, which is invariant, is stable under the action of G.
What's the relation between small f and V? V contains small f.
Thank you. Yeah, so a vector space which is stable under the action of G, and the f is contained in V. Yeah, so actually, if you think of the minimal subset that contains f, you just start applying. Remark that one should do here.
It is minimal if you have finite dimensional subrepresentation.
Yes, this means that we have finite dimensional subrepresentation. So that contains your given element. Yeah, so naively, if you take an element of f, some f, what you do? You just take all the elements of G, and pick up, consider linear combinations. What?
Is k of x of infinite dimension?
Usually, yes. Like polynomial rings. Yeah? То есть кольцо регулярных функций часто бесконечномерное. Над k.
Что на афинной, ну вот просто если у меня есть вся плоскость, то там бывают
Просто полиномы.
всех степеней.
Всех степеней, да.
Хорошо.
То есть над k, ну, как бы это конечно порожденная алгебра, но, то есть алгебра функций на афинном многообразии это конечно порожденная алгебра, но она как алгебра конечно порождена, то есть у вас именно вы берете образующие и пишете мономы от этих образующих. Поэтому, ну, как бы и сами мономы, они могут быть линейно независимы. Ну, в том смысле, of course, it can happen that X, for example, can be taken to be projective space. So this algebra of functions is just reduces to there are no regular functions except constants on projective space. So this this lemma is not so interesting, I would say. But there are some intermediate situations when the variety is not affine anymore and not projective. For example, open subset in affine variety could be not affine, but still you can speak about algebra of functions, or open subset in projective variety, or just there can be other situations when also some kind of intermediate situations. So, of course, what you should think of, you should take F, you should apply G, and if you are able to apply any elements of G, so this all elements of this form, I mean, you can apply a finite number of elements in the linear combinations, but you can allow any elements of G. So, of course, this form minimal G invariant subset, since I just can multiply it by HA and put it redenoted by HI. Yeah? So, so this will be invariant under the group action. However, yeah, so you pay the price that you have to take all elements of the group to be just to appear in this linear combination. So a priori you do not know, and we denote this by as the linear span of the orbit. Yeah, so you just take the function f, take its orbit as you apply all the elements of G to it by this action, and then you take all linear combinations. Of course, it can happen that it is, so it is minimal G invariant subset containing F, but a priori it can be infinite. But it can be infinite. So you have to argue somehow different, and the idea is to use, of course, the algebraicity of this action that we haven't covered so far. And what is the, so here you have the action map. Yeah? And this action map has a pullback map. Yeah, so this. Yeah, so and of course it maps Gx into the point in its action, applying action G times X. And you have a pullback map here, which is just the map from regular functions of X to the corresponding tensor products. Yeah, the functions on the product of affine variety is just a tensor product of the functions. And you notice that...
and what is G and affine variety? There are two varieties, G and X, and so...
no, algebraic varieties. I mean, let G be affine, but X is algebraic. Yeah? So affine group. But X is arbitrary algebraic. Okay?
So restatement for all. Are only for
I mean, this, yeah, so let it be any algebraic group. The problem is that, for example, there is the type of groups that cannot act non-trivially on affine space. So just yeah. So if actually it can happen that the map is trivial, the action is trivial. So for this, just I have said about affine because this has more sense in affine case and a little bit less in just general case. So if you have this map, and what does it mean? Yeah, so it is this map means that just this is how you are writing down the pullback map. This means that you have to take this map is just taking the function here and applying it to the argument. So just taking the pullback is you apply it to the function f, and you are applying it then to the argument gx, meaning that you just take f and apply it to the result of the action of g times x. Yeah, so this is by definition. And if you think of the pullback as the map from k of x into this product, it is just maps your function to the tensor product. So you decompose it into finite number of combinations, Fig tensor. So this means that you are the pullback of your function is just decomposed in the Fi tensor phi I, where you have in the tensor product in the sum corresponding to the in the tensor product you have only finite number of factors. So phi I belongs to k of x, k of g, and psi I belongs to k of x. And so if you are thinking how you evaluate it on gx, yes, so you evaluate this kind of functions in the tensor product. So this is just evaluation is written here. Yeah, so it is just applying fi to the elements of g and psi I to the elements of x and multiply them. Yeah? So this is just by definition of the action that associates the functions on the tensor product. So how you associate this just the functions on g times x is just so you are able to apply the functions on this to the element of this tensor product. So you are able to construct having the element of this tensor product, the function on g. And it is written precisely as follows. So this function on g of x, you apply the elements of g. And to this factor that is a function from k of x, you apply the element of x. And you take these products and the linear combinations. And you see here, yeah, so you see precisely as follows. So just yeah, so this just Yeah, so you see precisely as follows that just this collection of these functions doesn't depend on G. Yeah? So from the this can be viewed. So if you think of this as a function on X, so if you fix G and view it as the function on X, then you see that just this, if you so this decomposition in the tensor product for free gives you the following. So these are now, if you fix G, these are numbers. And this is a fixed collection of functions on G that doesn't depend on that does not depend on G.
It means that our GF subspace generated by Phi.
Yes, so this means precisely that if you look at all the linear combinations is I mean, this tells you the following. So this tells you that precisely this minimal subset, G-invariant subset, which is just GF, minimal G-invariant subset, G-invariant subset. So which is just the collection of pullbacks of, you can just think of this G or G inverse, so that doesn't matter. So this where G runs over all elements of G. I do not claim that this phi i's are precisely, so they form a G invariant subset. But at least this is contained in the finite dimensional subset. Yeah. So contained
Why does it come with
in
subset in finite dimensional?
what?
Why did we conclude that the subset GF is finite dimensional?
I mean, all these functions are written as linear combinations in terms of finite basis. So this, что?
Почему фи это их конечное число?
Ну, потому что это что такое? Это мы берем f, применяем к ней pullback, и это такая...
Конечным количеством полиномов.
Нет, фиита просто это конечное число. Вот это вот фиита, это, ну, это элементы в тензорном произведении.
Фиита это
Да.
координаты отображения фи. Из GX в X. Да?
Ну, фиита это просто функция на кат x, да? Ну как бы...
В общем, любой элемент тензорного произведения.
Ну, любой элемент тензорного произведения состоит из конечной линейной комбинации. Или...
Почему конечное число?
Ну, потому что вот эта линейная комбинация, она ни от чего не зависит, пока что.
Поняли, что фи
Мы взяли f, фиксированное f, и просто применили к ней pullback. Получили элемент тензорного произведения. И в нем ничего нету. Ну, как бы в нем пока есть только f и t, это элементы из g, ну, из алгебра функции на g. А это элементы из алгебра функции на x. Пока все. Ну, то есть вот этих фи конечное число. Теперь.
фи не строится по тому f, а просто
Нет, f и t строится по вот этому f просто применением фи со звездочкой. Вот.
Пожалуйста, в чем утверждение, которое доказывает еще раз?
Что найдется конечномерный модуль, G-инвариантный модуль, который содержит данный f.
Который сохраняется.
Ну, модуль, да, сохраняется, переходит в себя. То есть f не сохраняется, но что линейная комбинация вот таких элементов, где G пробегают все элементы из группы G, она конечномерная.
Can we estimate the number of
Of course, here no, because this depends on the action. Yeah, I mean these are infinite dimensional spaces, yeah, so you cannot bound them by dimension of phi, but you do not need it. Yeah. I mean different f can be in the problem is that different f can be in the modules of different dimension, and you clearly see it. If you have polynomial ring, if you have taken the polynomial of sufficiently high degree, homogeneous one, it will be contained in the set of all homogeneous polynomials of sufficiently high degree, but the degree is not bounded, the dimension of the space is not bounded. So this number of summands highly depends on where you take f, in which.
For example, if I take f equals x plus y.
Ну, тогда он будет степени 1. Ну, в смысле, лежать в однородных полиномах степени 1.
The number of fi equals the degree of f.
Размерности полиномов степени меньших, чем степень f. Ну, как бы, но это для той алгебры, для которой написано, ну, я как бы, как пример, но, так сказать. Yeah, so you just take this, you apply this function and you just decompose, да? А потом мы должны проинтерпретировать это, да, что мы применяем вот эту функцию. Что такое применить функцию к элементу G на x? Вот я хочу вот это равенство проинтерпретировать в терминах, ну, как бы аргументов, в терминах действия. Ну, как бы вот этот pullback, примененный к чему применяется pullback? So where do we apply pullback? To the pair g of x that are elements from g and x. Yeah? So how do I apply pullback? I take the image of this map and apply the function. Yeah?
So you want to make a map from polynomials to polynomials using pull element, yes?
Yes.
So it can be denoted just as pullback of phi with like.
Yeah, so it is denoted, yeah, so as a pullback of phi action map of phi of gx, and it is just applying f to the image of gx, which I just denote as an action, g times x. Yeah? And if I do the same from this side, if I already write down the function in this form as a function on g and x, I apply it to the pair of points g and x just by substituting g here and x here. So you get that this is from, if you fix g, then this is just a collection of scalars, so these are numbers, and these are collection of functions. Я прояснил?
And then the product firstly appears because it's like polylinear function.
The tensor product here just appears because it is a function on the product.
Polylinear.
Yes. Yeah, so there is so of course there is a poly, so you have the function, so you have a natural map, yes, from the function of from k of g times the functions on x. Yes, so you have a natural linear map which is just a product. Yeah, so you have taken function f here and phi here, and this is a product, f of g and phi of x. Yeah? So here it is precisely a polylinear map that corresponds to this tensor product. But the tensor product is the sum of such combinations of the functions, one of the on this sum and then one of the, on this factor, one on this factor and one of this factor. Da. Uh-huh.
I guess it is an isomorphism only if both G and X are affine.
No, I think not. Just. No, no. And what just yeah, so what we have here, yes, so you have decomposed it, and here you have only, so here you have yeah, so here you have this collection of functions, and here you have collection of scalars. So you see that the orbit is at least contained in a finite dimensional vector space. So this implies that GF, so dimension of GF is finite. And this is just, this is G invariant subset, invariant vector space. Okay. So, yeah, so, and when do we finish? Хорошо. So, and the next step is to just, I wanted to discuss, yeah, so if you have, yeah, so what about algebraic groups? I mean, what about affine algebraic groups? Yeah, so, just describing so characterization of affine characterization of affine algebraic groups. So here I want to say that affine algebraic groups are just a closed, they just form the, this is equivalent to say that they are closed subsets, closed subgroups in GLV. So if G is affine algebraic group, then it is can be realized as there exists rho homomorphism of G to GLV, homomorphism that just which is the injection, yeah, so which is injection, and G is a closed subgroup there. So rho of G is a closed subgroup. Yeah, so notice that if you have just automatically, if you have the group, yeah, so if you, the image of homomorphism is also algebraic group. Yes, so by previous lemma about constructibility.
It means that all fine groups are subgroups of linear, yeah?
Yes. Closed subgroups of linear groups. Yeah. So that's why sometimes people do not speak about affine groups, but about linear groups. So they call linear groups as just a closed subgroups of linear groups. So notice that if you have a row of G into H algebraic, so it is homomorphism. So algebraic homomorphism, regular. So it is a map of algebraic varieties, and the homomorphism of the groups. So notice that in the category of Lie groups, it is not clear that the image is a subgroup. Yes, so that famous twist of torus is just example of this situation. But in algebraic groups, we know that row of G is constructible subset. So that means that by our observation that row of G is closed subgroup. So this is more or less automatic. Yeah? So the only thing that we have to understand that our group will be injection. Yeah? So that our row will be injection. And how do we construct it? Yeah, so if you have G, then of course one of the most natural objects to act of G on itself. Yeah, so acts on G by right translations, for example. So right translations. This is to avoid taking inverse. So this means that G acts on the set of functions and notice that here in this set of functions you have the following. So this is finitely generated algebra if the group is affine. So finitely and this means that if it is a finitely generated algebra, then here there is a finitely generated set. So set of generators. And notice that so this set of generators sits in V, some finite dimensional G invariant subspace. So finite dimensional G invariant subspace. And how to check that the element G is trivial? Yeah, so to check that G inside G is equal to unit is equivalent to do the following. So just take different. I mean, you have this group G. Yeah, so it is precisely characterized by the functions. Yes, so G is trivial if and only if for any h, so gh is equal to h. Yeah? So this equality can be checked, so equivalently. So checking that the elements are equal is equivalent to say that the elements, all functions are, so for any f in K of G, f of gh is equal to f of h. Yeah? And so this is equivalent to say that, so our algebra is finitely generated. So this is equivalent to say that fi of gh is equal to fi h for any h and for any I. And this is just saying that so in other words, so you have an action of g on fi, and as the functions, they are equal. Yeah, so for any I. Yeah, so the element maps to 0 if and only if it maps the set of acts identically on the set of generators. So we just construct rho by the following. So G maps to GLV by the following. So you apply G to the collection of functions. Yeah? So you apply element G maps to application of this basics of the vector spaces. Yeah?
Sorry, is there, I was thinking.
Yes.
For me, that's what I don't understand what the proposition is about.
Yeah, so the proposition is the following. So if you have a fine algebraic group, yeah? So that means that it is an algebraic group which is a fine variety. Yeah? Then it can be embedded into the group of linear transformations as a closed subgroups. So it can be defined by the system of polynomials here.
How is it done?
It
Is it done on the V that was in the previous proposition, which is the invariant?
Yeah, so you have to notice two things. So first of all, you just have to construct only homomorphism to GLV because it is automatic. You just, the image of the homomorphism is a closed algebraic group. And if, so in order to apply V, you have to apply V a little bit more cautions. So you take action of G on its algebra of functions by translations. Yeah? And you notice that, so here in this algebra, there is a set of generators. And you put this set of generators inside the finite G invariant subspace. Just by putting this as a sum of this, yeah, so of the previously obtained spaces. Yeah? It is just a sum of the spaces chosen for each fi separately. It is also will be invariant. And if you take this subspace, now you have to understand that, so of course automatically you have a homomorphism from G into the set of, into the linear, so since your group preserves these functions and acts linearly, so notice that the group acts linearly on the set of functions just because f1 plus f2 applied. Yeah, so just here, of course, it is an evident stupid check, but it should be done. Yeah, so if you apply your function, then it is equivalent to lambda 1 f1 g inverse of x plus lambda 2 f2 g inverse of x. I mean, you have to know that
Pullback is linear.
yes, any pullback is linear. So you have but when you know it, you have automatically homomorphism of the group into linear transformations of this vector space. But you have to notice one thing, that this could be if you choose V badly without any assumption on the generators, then this map could have kernel.
For example, V equals to 0.
Yes. Yeah. A devastating example. Yeah, so, and in order to understand this, you have to understand the kernel of this map. So the kernel of rho is just the map of the elements of G that acts trivially, so such that G star of Fi is equal to Fi for any I.
Is it true that we want J-invariant subspace that contains all Fi's?
Yes.
Why such exist?
So the sum of subspace for Fi taken separately. Yeah, it's invariant on each summand.
RFI is a set of generators. Это как векторное пространство?
Нет, как алгебра. Вот это вот образующее как алгебра.
G вкладывается в алгебру преобразований. Представление алгебры, а не представление векторного пространства, правильно?
Нет, именно представление векторного пространства. Вот это образующая алгебра. Они порождают эту алгебру, но они сформируют, когда вы берете их линейные комбинации, то это конечное мерное векторное пространство. Вы его помещаете в какое-то другое векторное пространство. Но только инвариантное.
От набора F.
Да, so there was a good remark that this map depends heavily on the choice we have done here, but it is almost clear because you can embed any GLN into bigger GLN, for example, GL M as blockwise, yeah, and this embeds the closed subgroups here into the closed subgroups here. So this means that this embedding cannot be done technically unique, at least via this construction, yeah, but without any claim on minimality. Yeah? So, yeah.
The proposition is that this is an injection and the image is a closed subgroup in GA like D.
Yes, this is an ejection, but since it being closed, it is automatic because it is homomorphism. But the only thing that you have to understand is injection. But to check that it is injection, this is precisely why we are taking the set of generators here. Yeah, so because to check that the element is unit, it is equivalent to check that for any h, gh is equal to h. But checking that elements are equal is equivalent to evaluating all the functions of g on these elements. And they should have equal values. But evaluating functions is equivalent to evaluate only generators of the algebra. And evaluating generators is simply just applying G star of Fi. Yeah? So it can be written as just applying our action.
If our element is acting trivially on these functions, then it's
Unit, yeah.
on group.
On group.
So we are proving that there is no kernel.
Yes, yes. Yeah, so the kernel is such elements of G such that it fixes all the basic vectors. But this is equivalent to that evaluation, so that this holds for any functions in your group.
Я не очень понимаю, как
Да.
конкретно элемент ВЖ сопоставляем оператор.
Ну, вот, ну, у вас есть конечно-мерное линейное подпространство, да? Ну, вот это, вы берете элемент G, и он действует, ну, на вот этом, ну, на координатном подпространстве, ну, вот таким образом просто подставляет.
Но это же не базис V, это же не F.
Ну, в смысле, ну, как бы, ну, надо поменять базис на соответствующий. Ну, so we have to change. So
Ну, это как просто полтора.
yes, I mean that just it acts on all elements of V. I mean, so here you take, so the elements G acts on the functions. Yes, so on K of G. So this is V are the following. Yes, so G applied to F. You evaluate it on the element of H, yeah, of the element of the group. In order to distinguish functions on K of G, you evaluate it on the element of group. It is, by definition, writing down F of G inverse of H. So this function F maps to this function. It is a function on the group. And we claim that it fixes maps this vector space on this maps this vector space into itself. Yeah, so this just vector space V is a subset of K of G, and the claim was that G of V is a subset of V. So this means that G acts by linear transformations, because the G acts here as linear transformations on K of G. Yeah. So this is an action as linear transformations.
Is V more or less canonical, such that flow is
Ну, образующие они канонические? Нет. So the generators are not canonical. The minimal V containing generators can be taken canonical. Yeah? So just as minimal vectors, invariant vectors for subspace space containing the set of generators. The set of generators is not canonical by any means. And this, of course, tells you that G can be embedded completely differently in different GLVs. Like a group can have, the finite group can have many representations in which it embeds without kernel.
Many representations in SN, you mean, or vector spaces?
In vector spaces.
I think that this picture is like same
As,
any finite group in permutation groups.
Yes, and actually the reason that just you can just say that embedding permutation, you can construct a linear representation. Yeah, we are taking the group algebra of Sn. So embedding in Sn is equivalent to say about taking the corresponding linear permutation, a linear representation. Okay.
And we used that J is affine only when talking about that it's finitely generated out.
No, and here as well, that in order to check that so this was important part, I mean, that's why I have talked about this, that in order to, on a fine variety, you can check that the elements are equal. So let me state it explicitly as the statement. So just a remark, yeah. So if X is affine, to check that X, the point of X and Y, X is equal to Y, is equivalent to check that f of X is equal to f of Y for any f inside KFX. So this means that, so this is a property of separating points by the regular functions, and this property is, it doesn't hold if if the functions are only constants. Yes, on projective space you have no chance to do this. And this is quite important here. So yeah.
And this can be proved.
Well, sometimes the algebra is still, I mean, and for, if you take this for a Abelian variety, for which is projective the variety, closed projective variety, then this algebra functions will be trivial. So of course it will be finitely generated, but there is no reason of speaking about inclusions.
This, it's enough to check.
This one?
Now it's not obvious.
For you. Yeah, but we almost proved it because we can reconstruct the fine variety via its embedding of the generators. Yeah, so just f1 of x, fk of x, yeah, where fi are generators. This is more or less this construction. This is closed embedding, and this results in looking at the following. So if it reduces to, I mean this, if you have embedded X into the affine subspace, this reduces to saying the following on the vector space, just if V is a vector space. So here X is a closed subspace in vector space. So this is closed subvariety embedding. So here already in the vector space there exists a linear function such that L of x is equal to 0 and L of y is equal to 1. So when you embed it as a closed subset, you can just distinguish two different points by the linear function. But of course, linear function, so the non-trivial fact that a linear function, so this is a closed embedding, so all functions on x obtained as restrictions on functions on v. So that linear function gives you really a regular function on x. So this is slightly non-trivial thing, I mean, that you use here, but more or less it is trivial.
So we can just say that this map is embedding yields that like on different points some fi's will take different values.
Yes, yes. Yeah, it is. It's not. I mean, just to check. It can happen that it is a set theoretical embedding, but not the embedding as on the set of algebras of functions. Yes, so that the map is bijective on the set of in algebraic geometry. The map can be bijective on the set of points, but not even so even. It's not isomorphism on the set from the viewpoint of the closed subsets. So the pullbacks on the algebra will be non-trivial map. Okay. So maybe it's going to a point to stop, and next time we shall start with constructing homogeneous spaces, because we shall address to the following problem. So we shall consider G mod H. So the orbit space of so the set of cosets has a natural structure of algebraic variety, and we shall discuss how to give it. Notice algebraic variety, but not a fine algebraic variety. So thank you.
Thank you very much.
Mm-hmm.